Hello, class. Just waiting for a couple more people to join up. All right, so I'm going to go ahead and get started. Hope everyone's doing well today. So last time we discussed the effect of magnetic fields on charged particles. Okay. And what we learned was that the magnetic force can be written as QV cross B, where Q is the size of the charge, V is the velocity vector of the charge, and B is the magnetic field vector that the charge is experiencing. And so this is really equivalent to two different rules, okay? So the first rule is for the magnitude of the magnetic field, which is going to be the magnitude of the charge times the magnitude of the velocity times the magnitude of the magnetic field times the sine of the angle between velocity and magnetic field. So that's the rule for the magnitude. And then to get the direction, that's a strange way of saying hello. It's hanging quite well. Thank you. And then to get the direction, we used the right-hand rule. So I encourage you to review that if don't remember it. And then we learned that magnetic fields cause charges to move in circles. And the radius of that circle is mv over qb. We also learned that the magnetic force can only redirect particles. Okay, it cannot do any work. It can only redirect. All right, so this time what we are going to learn is Coulomb's law, basically what's called the Biot-Savart law. Biot-Savart. It's French. I think it's two people, I'm not sure. Or it could just be one person with a hyphenated name. I'm not really sure. Biot-Savart. Okay? Law. So try not to sound like a hick when you say it, and say Biot-Savart. It's Biot-Savart. Okay? Which I like to call it the BS law. And it's basically like Coulomb's law, but for magnetism. All right. So that's essentially what it is. So we're going to learn how to calculate the magnetic field. So last time we learned what is the effect of the magnetic field, and we assumed that the magnetic field was a given. And then now we're talking about how do we get the magnetic field in the first place, okay? And so the first thing I'm going to say is that electric current, which is denoted by I, is the source of magnetism. So flowing charge is the source of magnetism. That is how you get magnetic fields. Okay, if you don't have electric current, then you're not going to have magnetism. Okay. And then the next thing, remember how I said that cross products appear all the time in magnetism? So oh my gosh, I got a big yawn incoming. And so let me just review the cross product really fast. One more time. So let's suppose you have A cross B. The magnitude of the cross product, so the magnitude of A cross B, is going to be the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. Okay? To get the direction, you use the right-hand rule, which is where you put your pointer finger. So you use your right hand. You put your pointer finger with the vector A, so the first vector. Your pointer finger is with the first vector. Okay? It matters which order. Okay? A cross B is not equal to B cross A with cross products. It's not commutative. Remember how addition is commutative, like 3 plus 4 is 4 plus 3. 3 times 4 is 3 times 3, but with vector cross products, A cross B is not equal to B cross A, all right? And so it matters which finger you put with which vector. Pointer finger with A, middle finger with B, and then your thumb is with A cross B. All right, so that is how we can get the direction of it. Okay, so what I want to imagine is that we have a wire like this, okay, and that wire has current. So the current flow always has a direction, right? So what I want to talk about is a vector, which I will call dl. All right. And so the dl vector. And so the magnitude of dl, so basically what we want to do, if we want to talk about dl, is we look at a little tiny segment of wire, okay? So the magnitude of dl is equal to the length of the tiny segment of wire. Okay. And then the direction of dl is equal to its tangent to the wire in the direction of current flow. Okay, so that's the direction of it. So dl is going to point in this direction right here. All right, dl is going to point in this direction right here. dl is going to point in this direction right here. So it's tangent to the wire in the direction of current flow. Okay, and then we have another vector called r hat. Okay, and because it has a hat, it's a unit vector. So the magnitude of r hat is 1, of course. And r hat points from the segment of wire to where we want to calculate the magnetic field. Okay, so let's say that I wanted to calculate the magnetic field right here at point P. All right. Then the r hat vector for right here at this location is going to point from that segment of wire to the point P. So that's r hat. All right. From the segment of wire to the point P, so that's r hat at this location. From the segment of wire to the point P, so that's r hat at this location. So as we look at different spots along the wire, because the wire is curved, all right, we're going to have different directions for r hat. We're going to have different directions for dl. Okay. And then r, just with no hat over it, is the distance from the segment to the point P. So r is going to be that length right there, or it's going to be that length right there, or it's going to be that length right there, etc. Okay, so now we are in the position to state the Biot-Savart law. All right. The Biot-Savart law is mu naught I over 4 pi times the integral of dl cross r hat over r squared. Okay, and now because wires are typically loops, right? If you're going to have current flow, the current flow can't just stop. It's a loop going around the wire. We usually put a circle on this. Okay. So mu naught is called the permeability of free space. So if you recall, epsilon naught was called the permittivity of free space. Mu naught is called the permeability of free space. And it's another constant of nature. It's not really an independent constant, as you'll see in just a second. Mu naught is equal to 4 pi times 10 to the minus 7 Tesla meters per amp. Okay, so that is the value of the permeability of free space. So it's an exact value. So it's not really an independent constant of nature that's separate from epsilon naught. Okay. So actually, there's only one constant of nature. It's just that because of the units we've chosen, this constant also has to appear. Okay. And in fact, I'll just do a fun little calculation for you guys. What if I did 1 over mu naught epsilon naught, and then I square rooted it? So that would be the square root of 1 over 4 pi times 10 to the minus 7 times 8.85 times 10 to the minus 12. All right, so let's work out what that is. So I have 4 times pi times 10 to the minus 7 times 8.85 times 10 to the minus 12. And then I do 1 over that. And then I do square root of that. And that is just about 3 times 10 to the 8th meters per second, which is the speed of light. So really, there's only one constant. It's the speed of light. Okay? And just because of the way we've written the equation and because of the units, you have these epsilon naught and mu naught. But really, it's all just talking about the speed of light. So yeah. So let's. So this is the topic for today's lesson. Okay. Is the Biot-Savart law, and also for the next lesson. But so we're going to work on circular arcs today. Today's lesson is about circular arcs and how to calculate the magnetic field due to circular arcs. So let's say we have a full circle. All right. And then that circle has a radius, which we will call big R. All right. And let's suppose it carries current in the clock or in the counterclockwise direction around this loop. Okay. So it would have to have a battery or something to drive the current without it stopping. Or it's a superconducting loop. I don't know. And what we would like to do is we would like to calculate the magnetic field at the center of that circle. Okay? So let's pick a particular point on this wire. All right, and let's think about what is DL and what is R hat. So DL is going to point tangent to the loop. All right, and then R hat is going to point towards from the segment of wire to where we want to calculate the magnetic field. So that would point from the edge of the circle towards the center. So that's R hat. And we can see that the angle between them is 90 degrees. All right. So if I were to do DL across R hat, all right, well, let's just do the magnitude first. So the magnitude of DL cross R hat is going to be the magnitude of DL vector, which a lot of times we will just write the magnitude of DL vector as just DL without the arrow over the top. Okay, so it's equal to the magnitude of the DL vector, which we just write it as DL with no arrow, times the magnitude of R hat. R hat is a unit vector. It has a length of 1. Times the sine of the angle between them, and there's a right angle between them, which is 90 degrees. The sine of 90 degrees is 1. So we just get DL times 1, which is just DL. Okay? So, and then we have to get the direction. So I've got to put my pointer finger with DL. My middle finger goes with R hat. So hopefully you can see. Look at, see how, ooh, that camera angle is perfect. See how DL goes that way, R hat goes this way. And then my thumb, you can see, is pointed up right towards the camera. Okay? And so that means that DL cross R hat points out of the page. And we could try a different location on the circle and show that we get the same answer no matter where we are on the circle. Okay, so what if I chose that point? I put my pointer finger with DL, middle finger with R hat, my thumb is going out of the page. Okay, so the direction is going to be out of the page. Okay, and then that would be in the so-called Z hat direction. We're going to call Z hat out of the page. So that what that means is that DL cross R hat is equal to DL magnitude times Z. All right? And then if we look at the other thing in the Biot-Savart law, is we also have over R squared. And so little r squared is going to equal big R squared, because every point along the loop is the same distance away from the center of the circle. That's what a circle is. Okay? So this is going to be a constant. So when I plug this in, okay, so when I plug this in to the, when I plug this into the Biot-Savart law, which is, so I'm trying to get the magnetic field at the center. It's mu naught I over 4 pi times the integral around the loop of dl cross r hat over r squared. Okay, so I'm going to plug in this right here, and I'm going to plug in this right here. All right, so 4 pi. Okay, so now z vector is a constant, and as I said, big R is the radius of the circle, which is a constant. So that means that I can factor both of those out of the integral. So I have mu naught I z over 4 pi r squared times the integral around the loop of dl. So this is the sum of lengths around the loop. The sum of the lengths around the loop. That's the same thing as the circumference. That's the same thing as the circumference, is it not? So this integral is going to be equal to the circumference of a circle of radius r, which is going to be 2 pi r. All right. So we're going to get mu naught I z hat times 2 pi r over 4 pi r squared. So then canceling out factors of r and pi and stuff like that, we get mu naught I z hat over 2r. And that is the magnetic field at the center of the circle. Okay. What if we didn't have a full circle? Okay. Well, in that case, so like what if we had a, I don't know, a circular arc of current? All right. So here's the center of the arc. Okay. So it's like a slice of pizza. All right. And we wanted to know what's the magnitude of the magnetic field due to this circular arc. Well, in that case, you could go through the entire calculation and it would be exactly the same as before, only when we're summing the lengths, we wouldn't go all the way around the circle. We would only go around the arc, okay? So let's say that the arc is theta radians, okay? Then the length of this part of the arc would be theta r. Okay, if you have a full circle, that's 2 pi radians, so you get 2 pi r. All right, and so everything else in the calculation is the same, except for the length of the arc. We don't go all the way around the circle. And so what you would get if you have an arc, the magnetic field at the center, if you only have an arc, is going to be mu naught I times z hat over 2r, but we multiply that by theta over 2 pi, right? So if it's a full arc, theta is going to be 2 pi, so you have 2 pi over 2 pi, and you get 1, which is the same, gives you the same result as before. But basically, you're multiplying the full circle result by the fraction of a circle that you have. So if you have half a circle, you would multiply this by 1/2. If you have a quarter of a circle, you multiply this by 1/4, etc. Okay? I wanted to point out an important fact. Which is this. So what if we have a segment of wire that is straight? And so the next lesson we're going to be talking about straight segments of wire, not circular arcs. But there is an important fact that you will need in order to do today's lesson. So what if I have a point here, let's call it P1, and what if I have a point P2? Like that, all right? And then I have a segment of wire right here that I want to figure out what is DL cross R hat. So what if I was talking about point 2? Well, my DL points in the direction of the wire, which is to the right. And then my R hat vector also points from the segment of wire to where I want to calculate the magnetic field. So it also points to the right. Okay? Or similarly, if I wanted to calculate the magnetic field at point P1, I would again have DL going this way. And then I would have my R hat vector going in the opposite direction. Okay? So in this case right here, we have theta equals 0. Right? When I say theta equals 0, I mean remember that the magnitude of DL cross R hat is going to be magnitude of the first times magnitude of the second times sine of theta. And the sine of 0 degrees is 0. Okay? Here we have theta equals 180 degrees. The sine of 180 degrees is also 0. Okay? So in both of these cases, you have the angle is such that the cross product is 0. Okay? So basically what that means, the important fact is this. And remember, the Biot-Savart law has DL cross R hat in it. So basically, there is no magnetic field directly in front and directly behind a wire. Okay, so for example, there's a homework problem where you have a loop of wire, because wires are always loops. Okay, I hear you, Bug. Right, hear you, Hazel. When the dogs get thirsty, they start flipping their water bowls over. I hear flipping water bowls right now. Okay, so you might have a loop of wire that does something like this. Okay. And so you're trying to calculate the magnetic field at the center. All right. So you can see this is made up of 2 semicircular arcs and then 2 straight arcs. Okay, the straight arcs, see how the center of the circle is directly in front of this wire and directly behind that wire segment. So the straight segments of the wire don't create any magnetic fields at the point C. All right, it's only the circular arcs that create the magnetic field at the center. Okay, so you're going to need that for the quiz today. All right, dudes and dudettes,